Hello, Accelerated Chemistry students. This is Ms. Crisafulli, and this is your Chapter 21, Section 1 video notes all over electrochemical cells. So let's first start talking about electrochemical processes. So chemical processes can either release energy or absorb energy. The energy can sometimes be in the form of electricity. An electrochemical process is any conversion between chemical energy and electrical energy. All electrochemical processes involve redox reactions. Electrochemical processes have many applications in the home as well as in industry. Flashlight and automobile batteries, silver plating of tableware, biological systems are all examples of how electrochemical processes are used in our everyday life. Let's review redox reactions and the activity series. So zinc metal oxidizes spontaneously in a copper ion solution. The net ionic equation involves only zinc and copper. So here's our net ionic equation. So we're going to have zinc solid plus copper 2 plus, which is going to be the ion from solution, is going to go to zinc 2 plus plus copper solid. And let's look and review how to assign oxidation numbers to these. So zinc is a metal by itself, so its oxidation number is 0. Copper 2 plus is going to be an ion, so its oxidation state is going to be the charge of the ion. Zinc 2 plus, again, is going to be zinc 2 plus, and copper solid is going to be 0 because it's in its elemental state. Now remember, once we assign our oxidation numbers, we're going to look at who's losing electrons and who's gaining electrons. So electrons are going to be transferred from zinc atoms to copper atoms. So our zinc is going to go from zinc solid to zinc 2 plus, and it's going to transfer those 2 electrons to the copper 2 plus that's going to be in solution, and then that copper is going to plate on top of the zinc. And so we're going to have a copper coating on top of our zinc. So what does that look like? So zinc atoms lose electrons as they are oxidized to zinc ions. So our oxidation reaction, remember, we have electrons being lost, so they're going to be on the product side. Then the copper ions in solution gain those electrons lost by zinc, and our reduction reaction is going to look like this, because remember, reduction gains electrons. And so we have copper 2 plus our 2 electrons going to copper solid. If we look at the activity series of metals, for any 2 metals in the activity series, the more active metal is going to be the one that's more readily oxidized. So when we compare zinc and copper on the list, zinc is above copper. So that means that zinc is more readily oxidized than copper is, which zinc is dipped in. When zinc is dipped into a copper 2 sulfate solution, the zinc is going to become plated with copper because the copper is going to take the electrons that zinc is giving off to make copper solid, and it's going to plate the zinc with a layer of copper. When a copper strip is dipped into a solution of zinc sulfate, the copper does not spontaneously become plated with zinc. This is because copper metal is not oxidized by the zinc ions. So when we look at electrochemical cells, when a zinc strip is dipped into copper 2 sulfate, electrons are transferred from zinc atoms to copper ions. This flow of electrons is an electric current. An electric current can be used to produce a chemical change. Any device that converts chemical energy into electric energy or electrical energy into chemical energy is an electrochemical cell. Redox reactions occur in all electrochemical cells. A voltaic cell is an electrochemical cell used to convert chemical energy into electrical energy. Electrical energy is produced in a voltaic cell by a spontaneous, means it happens on its own, redox reaction within the cell. So let's talk about how we construct a voltaic cell. A voltaic cell consists of 2 half cells. A half cell is one part of a voltaic cell in which either oxidation or reduction occurs. Remember, oxidation is loss of electrons and reduction is the gaining of electrons. A typical half cell consists of a piece of metal immersed in a solution of its ions. So that means that we have to have a solid piece of metal in a solution that has that metal's ions present. The half cells are connected by a salt bridge, which is a tube containing a strong electrolyte, which will allow electrons to flow. Often potassium sulfate, potassium nitrate, anything that has a metal and a non-metal is going to be in our salt bridge. A porous plate may be used instead of a salt bridge. The salt bridge or porous plate allows to pass from one half to another, but prevents solutions from mixing completely. So if we look at our salt bridge here, and if we look at this, in this voltaic cell, the electrons generated from the oxidation of zinc to zinc 2 plus flow through the external circuit or the wire onto the copper strips. So they flow from the anode, which is going to be the negative side, to the cathode, which is going to be the positive side. The anode in this case is going to be the zinc because it's losing electrons. And the cathode is going to be the copper because that's where our electrons are being gained. The driving force of such a voltaic cell is a spontaneous redox reaction between zinc and copper. Remember, zinc was higher than copper on the activity series, so zinc is going to be more reactive and more readily able to lose its electrons than copper is. The zinc and copper strips in voltaic cells serve as our electrodes. An electrode is a conductor in a circuit that carries electrons to or from a substance to another metal. The electrode at which oxidation occurs or the loss of electrons is the anode, and that is where our electrons are produced. The anode is labeled as the negative electrode in a voltaic cell. The electrode at which reduction occurs is called the cathode. Electrons are consumed at the cathode in a voltaic cell. The cathode is going to be labeled with a positive electrode. The electrochemical process that occurs in zinc and copper voltaic cells can be best described in a number of steps. And always these steps occur at the same time. So step 1 is the electrons are produced at the zinc strip according to the oxidation half reaction below. So zinc is going to go from zinc to zinc 2 plus. And so the zinc 2 plus ions are going to go into solution. Those electrons are going to flow from the left beaker to the right beaker, and they are going to light up that light bulb as they go across. Step 2, the electrons leave the zinc anode and pass through the electric circuit to the copper strip, and we're going to see that because the light bulb is going to light up. Electrons interact with copper ions in solution, and then the following reduction reaction occurs. So those electrons are going to be deposited onto the copper strip, and so that is going to get a negative charge. So we want to make sure that our solutions are neutral constantly. So the copper ions that are in solution are going to go and plate themselves on that copper electrode. And then to complete the circuit, both positive and negative ions move through aqueous solutions via the salt bridge. So we want to make sure that this whole thing is neutral constantly. So the only thing that's going to happen is that our salt bridge is going to transfer our ions where they need to go, so that way we keep the solution neutral. The two half reactions can be summed to show the overall reaction. Note that our electrons must be canceled. So we have zinc going to zinc 2 plus, that's our oxidation reaction. We have copper going to copper 2 plus, going to copper solid, that's our reduction reaction. So we're going to cancel our electrons and we're going to add up these two things, and that is our overall reaction that we started talking about at the beginning of the video. So let's talk about representing electrochemical cells. So we can represent the zinc copper voltaic cell by using the following shorthand form. So we have zinc solid, and then we have a single bar going into zinc sulfate because that's where our zinc 2 plus is coming from. Then we have copper 2 sulfate, which is going to be what's in our beaker, our solution, and we have the copper solid, which is going to be the copper piece. The single vertical lines indicate boundaries of phases that are in contact. So we have zinc with zinc sulfate and copper sulfate with copper. The zinc and the zinc sulfate are going to be in one beaker. The copper and the copper sulfate are going to be in another beaker. The double vertical lines represent the salt bridge or porous portion that separates the anode compartment from the cathode compartment. And the half cell that undergoes oxidation or happens at the anode is written first to the left of the double vertical line. So current applications that use electrochemical processes to produce electrochemical energy include dry cells, lead storage batteries, and fuel cells. Let's talk about dry cells. A dry cell is a voltaic cell in which the electrolyte is a paste or a solid. So here's an example on the bottom left. So in one type of dry cell, a zinc container is filled with a thick, moist electrolyte paste, magnesium 4 oxide, zinc chloride, ammonium chloride, and water. A graphite rod is embedded in the paste. The zinc container is the anode and the graphite rod is the cathode. So that means the zinc is going to be losing its electrons and the graphite rod is going to be gaining its electrons. The thick paste and its surrounding paper liner prevent the contents of the cell from freely mixing, so a salt bridge is not needed. The half reactions for this cell occur as below. We have this oxidation and this reduction happening. Our reduction reaction is a little more involved, but that's okay. The graphite rod serves only as a conductor and does not undergo reduction, even though it's at the cathode. Dry cells of this type are not rechargeable because the cathode reaction is not reversible. The alkaline battery is an improvement of the dry cell. So the reactions are similar to those in the common dry cell, but the electrolyte is a basic KOH paste. This change eliminates the buildup of ammonia gas and maintains the zinc electrode, which corrodes more slowly underneath basic or alkaline conditions. Now let's talk about lead storage batteries. A battery is a group of voltaic cells connected together. A 12-volt battery consists of 6 voltaic cells connected together. So each cell produces about 2 volts and consists of a lead grids. The anode is packed with spongy lead. The cathode is packed with lead 4 oxide. And the electrolyte for both half cells is sulfuric acid. Using the same electrolyte for both half cells allows the cell to operate without a salt bridge or porous separator. The half cell reactions are as follows. So as oxidation, we have lead going to lead solid, going to lead 2 plus, and then we also have lead 4 oxide going to lead 2 plus as well. The overall spontaneous reduction reaction that occurs is the sum of the oxidation and reduction half reactions. So here is the overall reaction, and then that would be what we got when we added up the 2 half reactions. So this equation shows that lead 2 sulfate forms during discharge, and the sulfate slowly builds up on the plates, and the concentration of sulfuric acid of the electrolyte will eventually decrease. The reverse reaction occurs when a battery is recharged. So we can flip that reaction around and go in the opposite direction. This is not spontaneous, so to make the reaction proceed as written, a direct current must be passed through the cell in the direction opposite of that current flow during discharge. So when we're looking at a car, when we start the motor, we're going to have a discharge of electrons, and then we are going to have our reactions proceed in one direction for our voltaic cell and for our electrolytic cell, depending on where we're looking at in our car. Let's talk about fuel cells. Fuel cells are voltaic cells in which a fuel substance undergoes oxidation and from which electrical energy is continuously obtained. Fuel cells do not have to be recharged. They can be designed to emit no air pollutants and to operate more quietly and more cost effectively than a conventional electrical generator. So here's a picture of a fuel cell. The hydrogen-oxygen fuel cell is a clean source of power. The only products of the reaction are liquid water. Such cells can be used to fuel vehicles. There are 3 compartments separated from one another by 2 electrodes. The electrodes are usually made of carbon. Oxygen is the oxidizing agent from the air, flows into the cathode compartment, and hydrogen, the fuel, flows into the anode compartment. The half cell reactions are as follows. So oxidation, we have hydrogen making 4 H pluses, and the reduction is we have oxygen going to O2 minus, and the overall reaction is an oxidation of hydrogen to form water, which is H2 plus O2 gives 2H2O. And that is the end of your Chapter 21, Section 1 video notes all over electrochemical cells. And as always, all of the information on these video slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbooks, resources, CD, and pearsonchem.com. Thank you so much. Have a great night.